How you look at a landscape depends on a lot of things: your background, your interests, and sometimes even your goals. For a geologist, landscapes are not just beautiful and inspiring. Landscapes can be informative, telling you about everything from natural resources to what it would be like to build something there. You can even understand the geology behind what an artist has captured in a landscape painting. Within an overall landscape, geologists like to talk about individual landforms. For example, a dune is part of a desert landscape. A hoodoo is part of the Badlands landscape. A moraine is part of the glacial landscape. When we study these features, we talk about a specific set of processes that resulted in their formation. I talked about them in the first lecture. The Earth's surface is a product of internal forces, like plate tectonics, and external forces, like rivers, wind, and glaciers. When you start to get a larger feature, like Waimea Canyon in Hawaii, we begin to move into discussions of landscapes and all that is involved in the creation of a landscape. But geologists try not to get hung up over having a sharp line between landforms and landscapes. Instead, geologists talk about geomorphology, which is the study of landscapes and their individual landforms. Literally, the term geomorphology means the study of Earth forms. And what's fun is, as you learn more geomorphology, you'll find yourself not just seeing features, for instance, a hill, but describing them in an explanatory way. For example, a hill can be a place where the rest of the landscape has been worn away, like Sugarloaf in Rio or Ayers Rock in Australia. In that case, a hill is called a residual upland. In other places, a hill might be the result of having a bedrock cap at the top of it. That's a resistant unit that is preventing the top from being eroded. Then that might be called a butte, a mesa, or a plateau, depending on the size and shape of the feature, and to some degree, local preference. The old cowboy definition says that if you can graze cattle on it, it's a mesa, but if you can't, then it's a butte. The thing to understand is that there's a size and process relationship. You can envision that a plateau will weather to a mesa, and a mesa will weather to a butte. The larger point is, you don't just describe shapes and slopes. You learn to interpret the processes that created those shapes and slopes, which can also offer insight into how that shape may change in the future. Geomorphology is a wonderful science to learn for the traveler. Geomorphology has an interesting past. French and Swiss scientists began to see the relationship between rivers and landscapes in the late 1700s, and those observations influenced the development of modern geology. But the science of geomorphology became a full-fledged subfield of geology with the exploration of Western North America after the Civil War. North America provided unmodified examples of diverse landscapes in diverse settings, and those landscapes called out for an explanation. To mention just three examples: the unique topography of the Basin and Range, the origin of fluvial features like the goosenecks, and the Great Salt Lake and the history of Glacial Lake Bonneville that it formed from. Essentially, the West was a geomorphologic laboratory, and research developed rapidly. As more science was done, researchers began to see that landscapes developed as a result of specific causes. That is, a landscape wasn't at all arbitrary. For example, the Columbia Plateau formed as a function of multiple lava flows and river downcutting. As more work continued, geomorphologists began to quantify the relationship between process and landform. Niagara Falls was a great example. Frederick Wright's work in the 1890s estimated the retreat rate of Niagara Falls from its point of formation at the Niagara Escarpment to its present and larger position, occurring at a rate of roughly 3 feet per year. This work provided one of the earliest estimates for the timing of deglaciation in North America, which he estimated as 13,000 years ago, which was pretty good. We now think deglaciation began about 16,000 years ago, and such work continues today. In short, geomorphology is an easy and powerful tool to understand the world around you. With some careful observation and a little intuition, you can learn a great deal about your surroundings. So I'd like to give you a quick and dirty way to recognize different types of rocks, just by looking at the landscape. What we'll be looking for are cliff formers and slope formers. Let's look at the Rosengarten, a famous landform in the Dolomites of Italy. The top of this ridge is capped by a cliff former. Below it, there's a slope, then another small cliff, and then a long slope. The two cliff-forming rocks resist erosion, so they form extremely steep landscapes, cliffs. The slope formers erode easily and underlie the gentler slopes of the Rosengarten. The characteristics and classification of a rock is referred to as lithology. The word lithology literally means the study of rock, but has evolved to essentially mean rock type. Any lithology that resists weathering and erosion is called a resistant unit and will generate cliffs, or at least very steep slopes. Conversely, a lithology that weathers easily will be a slope former, with loose and crumbly slopes. If you're hiking in the mountains, you can tell when you're in a resistant unit, a cliff former, because trails will consist of switchbacks on steep slopes. Conversely, hiking gets easier on a slope former because slopes are less steep and there are fewer switchbacks. Let's look at an arid environment or places with little vegetation, which is where you can easily differentiate cliff-forming units and slope-forming units. When you're at the south rim of the Grand Canyon, you look across the canyon and you readily see slope formers and cliff formers. The north rim of the canyon is underlain by the Kaibab limestone. It's a very resistant unit and it forms very steep cliffs. In short, you can read the underlying geology from the shapes of the landscape. That's the power of geomorphology. In dry climates, limestone is a cliff former, but things change if we're in a wet climate, where limestone becomes a slope former and a valley former. Suppose you're in a wet climate like Virginia and looking out over the Shenandoah Valley, say from the Blue Ridge vistas of Shenandoah National Park. The difference is that limestone dissolves in humid climates that have abundant vegetation, so that the valley is a topographic low that is underlain by limestone. The constant production of organic acids together with the continuous flow of groundwater result in the steady dissolution of the limestone. Geology influences landforms in other ways. Let's go back to the south rim of the Grand Canyon. As you look across to the north rim, your eye is drawn to both the variations in lithologies and the slopes and the cliffs. The north rim is 1,000 feet higher than the south rim. So when you look from the south rim, you're looking at a wall. Now, check out the view from atop the north rim. The Grand Canyon experience is quite a bit different. Of course, there is a different vegetation and different climate on the north rim. That's certainly different. But as you look out over the canyon, your eye is drawn to the panorama of the south rim. You see a landscape interrupted by volcanic cones. For example, Humphreys Peak, which is recognizable by its distinctive shape and prominence on the flat landscape. And from the heights of the north side, you also find yourself looking down into the canyon. That exercise illustrates how tectonics and volcanics influence the landscape and how you view it. Both tectonics and volcanoes, through vertical displacement and buildup of newly produced igneous rock, command the horizon and make a landform more prominent. So tectonic setting and rock type both go into the formation of landscapes and landforms. William Morris Davis, the geologist most frequently associated with the establishment of geomorphology as a science, considered rock characteristics the most important factor in the development of a landscape. but Davis overlooked the complexity of geologic processes. There are many processes occurring at once. So over time, geomorphologists began to envision landscape formation as a function of 5 things. What are they? In addition to rock characteristics, climate has a big influence, and arid regions have very different landforms than humid regions. A third factor, influenced by rock type and climate, is topography. This is also called slope and aspect. Flat versus steep slopes will influence how much erosion occurs. South-facing slopes, sunny and dry, versus north-facing slopes, wet, cool, and shady, can have very different slope angle. A fourth factor is biota, that is, plants and animals. Plants produce organic acids that dissolve rocks. Various animals will also break up soil and rock materials. And human activity is also included in biota. Many geologists argue that in terms of volume of earth material moved, humans have become the most important geomorphic agent. Lastly, there's time. How long any of Earth's processes have been acting on a region will influence its form. These are the 5 big influences: geology, climate, topography, biota, and time. They can also affect one another, so they will really help you understand why the world around you looks the way it does if you keep them in mind. To be complete, I'll just mention extraterrestrial processes. Impacts from space are a distinct class of processes that result in a unique suite of craters and other impact landforms. The Moon is covered with examples of all sizes. From South Pole Impact Basin, which is the size of the US, to the Apollo Impact Basin, to the Scobie and Jarvis craters, down to the tiny craters inside them. Earth has experienced the same bombardment, but extraterrestrial landforms disappear quickly because of ordinary exogenic processes. The result is there are only about 100 mapped impact craters on Earth. Geomorphology can also be used to look at larger scale features as well, which are sometimes grouped into geomorphic provinces. Let's take a look at some geomorphic provinces around the US. If you look at a relief map of the eastern United States from Maine down to Georgia, it's easy to spot 2 very different geomorphic provinces. The Appalachians are the prominent features with rugged topography. The flat, featureless area to the east of that is the coastal plain. The Appalachians are a mountain range. In fact, it's a very typical mountain range in that it formed when 2 continental plates collided. The North American plate, rotating in a clockwise direction, converged on the Eurasian plate. This happened over the course of millions of years, culminating around 260 million years ago. As the plates collided, the continental crust was shortened by folding and faulting of thousands of feet of rock. The result was the formation of both a supercontinent, called Laurasia, and the Appalachian mountain range, which would have rivaled the Alps in terms of elevations of mountaintops. The Appalachian mountain range was once a far more rugged and spectacular landform, but over time it's been worn down. That's why it looks the way it does, and not like the Alps. In the time since the Appalachian uplands formed, the climate of eastern North America has been relatively warm. In addition, there's been lots of vegetation which resulted in the production of lots of organic acids, which over time has contributed to the weathering of the rocks. Frequently, a mountain range generates its own weather pattern, with localized rain and running water actively eroding those mountains. The result is the topography you see today. It certainly is still a highland, and you get the sense from features like Blue Mountain in Pennsylvania that these were once very large features. But the landscape evolves. The coastal plain, it's flat, or at least gently sloping. The coastal plain geomorphic province extends miles eastward from the present-day Atlantic shoreline to the foot of the Appalachian Mountains, called the Fall Line because there are frequently waterfalls there. How did that landscape develop? The answer lies in the age of the sediments that make up the coastal plain. They're all younger than the rocks of the Appalachians. The coastal plain formed after the Appalachians formed. Supercontinent Laurasia rifted apart not long after the formation of the Appalachian Range. As North America broke away from what is now England and Scandinavia in the north, and away from Morocco in the south, the rivers that eroded the Appalachian uplands carried sediment towards the newly formed ocean. These rivers deposited a thick accumulation of sand and gravel. Of course, that plain has been worn down with time, but essentially, it's been a relatively flat landscape since it was formed. During times of low sea level, like during the last glaciation 25,000 years ago, coastal plain sediments were cut by large rivers, creating the canyons you see at the edge of the continental shelf, like Baltimore Canyon, Washington Canyon, and Norfolk Canyon to the east of Delaware, Maryland, and Virginia. Now let's move westward to the central part of the United States. These central geomorphic provinces are called the interior lowlands. Drivers heading westward along Interstate 80 notice two things pretty quickly when they arrive in Ohio. First, it's relatively flat, and second, there's a lot of farmland. The interior portion of the United States is underlain by very ancient, stable rock called a craton. Cratons represent the very beginning of the forming of the North American continent. The word craton comes from the Greek word for strength. It was first used in the early 1900s to describe ancient parts of the crust that were old and had undergone multiple tectonic events, but were now stable. Once the stable interior of the North American continent took shape in the late Precambrian time, roughly 570 million years ago, major tectonism ceased. That's not to say the interior lowland was not affected by tectonics. Indeed, it has been, just not as dramatically as the continent's margins. But while the margins of the continent were undergoing mountain building, the forces from that tectonic activity compressed and thickened portions of the North American interior. However, even with those compressional forces, the center of the continent was little deformed. At various times, the center part of North America was covered by shallow seas, accumulating sediment in individual basins. But those sediment deposits were never deformed. The result is that a long interval of time represented by sedimentary rocks of varying thicknesses in different parts of the interior lowland. This time was followed by a long interval of erosion that resulted in a flat, low-lying landscape. Because the climate east of the Mississippi is relatively humid, thick soils formed on those flat-lying sediments and sedimentary rocks. The result was the breadbasket of the U.S. As you go further west, things change. Leaving Iowa and heading into South Dakota, the landscape is different. This is the Great Plains geomorphic province. It's still flat, but it's different. The elevations increase as you head westward. There's also a change in the underlying geology. Rocks are younger and have a very different depositional history than the underlying rocks to the east. Some were deposited in the western interior seaway 90 million years ago. Still others were deposited by rivers flowing from the west 15 million years ago. Traveling still further west, the Badlands, a clearly different landscape with flat-lying sediments, not solid rock, and stair-step river valleys characterized by distinctive and repeating slopes. What changed? Why so different? Two things happened. The first is that the climate changes. West of the Mississippi, you have a greater amount of evaporation than precipitation. You've entered a drier climate. The Rocky Mountains create a rain shadow, and the influence of the drier environment is apparent. There is also very different vegetation. Prairie and grassland dominate, and the soils are thinner. The result of drier conditions is a greater influence of intermittent precipitation and runoff. The incised valleys and the dry conditions created the Badlands that extend from the western Dakotas southward to Texas. The second thing that happens is that you approach the Rocky Mountains. The Rockies are another tectonic upland, just like the Appalachians. And as was the case with the coastal plain, mountains go up while sediment gets deposited on the flanks. The sediments of the Badlands were distributed by extensive river systems flowing from the Rockies as they were uplifted. Heading further west, you can't help but notice the Rocky Mountains are different from the Appalachian Mountains. The 5 factors of geomorphology. Remember? Geology, climate, topography, biota, and time have affected the landscape differently, causing the Rockies to be different from the Appalachians. The geology is different, but not so much that you would expect to see huge differences in the landscape. A tectonic process called folding is more common in the Appalachians than in the Rockies. Conversely, another tectonic process called thrust faulting is more common in the Rockies. So a little bit different types of tectonics. Climate is drier in the Rockies. As a result of the drier climate, vegetation is different. We talked about limestone being a resisting unit in the west and a non-resistant unit in the east. Through much of the Rockies, there are uplands made of resistant limestone units. But more importantly, you also have a much younger mountain range in the Rockies. The uplift and formation of the Appalachian Mountains was essentially done around 250 million years ago. The Rockies were uplifted in several different stages, starting from 150 million years ago, but continuing to 40 million years ago, making for a much younger mountain range. West of the Rockies, you get into the Colorado Plateau. This large, relatively uniform upland with deeply incised rivers surrounds the Four Corners regions of the U.S. and is the location of many spectacular geomorphic features, like Monument Valley, Horse Thief Point, Bryce Canyon, the Painted Desert, the Grand Canyon, and many more. The geomorphology of the Colorado Plateau is really influenced by external processes like rivers downcutting and the erosion of slopes, while the mountains of the Rockies are dominated by internal forces like tectonic uplift. West of the Colorado Plateau is the Basin and Range geomorphic province. If you look at the Basin and Range, you can see a pretty distinct landform pattern. You have these elongate mountain ranges separated by mostly dry basins. The ranges trend in the north-south pattern, and there is no more than about 5,000 feet of relief between the mountains and the basins. Many of the basins have no drainage outlet, so during wetter climates, they contain large lakes. The Basin and Range geomorphology looks so different from the Rockies and from the Pacific Ranges to the west because each is the result of a different tectonic process. As I mentioned, the Rocky Mountains formed by thrust faulting. Rocks pushed up faults at a fairly low angle. The Basin and Range, on the other hand, is the result of steep, nearly vertical tectonics. It's like the mountains were blocks moved up and down. Geologists refer to it as block faulting. The mountains moved up and the valleys moved down. North of the Basin and Range is the Columbia Plateau, which is one of the geomorphologically youngest landscapes in the U.S. Volcanism has created a series of plateaus that are the result of a migrating hotspot. The oldest of these plateaus is in eastern Oregon, while the youngest is located 500 miles away in Yellowstone National Park. Yellowstone is the site of an enormous volcanic caldera that has not had a big eruption for 100,000 years. Yellowstone Lake sits in what was the central vent of a large volcano. To the west, the Snake River Plain formed in a series of volcanic flows. The remnants of volcanic cones stand out because they are so geologically young, only 6 million years old, while the rest of the area is flat-lying lake sediments called lacustrine sediments. Wagon trains used to use the volcanoes as a navigating guide when they traveled westward. Now that's practical geology. When you get to the mountain ranges of the westernmost U.S., you get an active tectonic zone where mountains are still being uplifted. and young rocks are being deformed. Hence, the rugged geomorphology of the Pacific coastal ranges, the Sierra Nevada, and the Cascades. Here, internal forces like tectonism and volcanics are part of daily life. There's one more large geomorphic province in North America, found in the middle of the United States, and that's the Precambrian Shield, sometimes known as the Canadian Shield. These rocks are exposed in northern Michigan, Wisconsin, and Minnesota, and they are geomorphic expressions of the craton. Geomorphologically speaking, there is no place in the United States where geologic time has had more opportunity to influence the landscape. The rocks remaining in the Precambrian Shield are some of the oldest rocks in the world. Approximately 3 billion years ago, microplates began converging to form a proto-North America. Over the course of the next 2 billion years, microplate collisions would result in the North American craton. Of course, the collision of microplates resulted in a great deal of tectonic uplift and the generation of substantial mountain ranges. But that all happened billions of years ago, and those mountains are long gone. What remains are the broad, low-relief dome of the Precambrian Shield, which formed those ancient rocks and then were worn down through time. In addition to surveying the major geomorphic provinces, we can also take a look at some great landscapes that have challenged both travelers and geologists in their diversity and complexity. The U.S. is really a remarkable geomorphology laboratory. Florida, for example, is in the east, but is not the coastal plain. It's got springs and lakes that you don't see on the coastal plain. What makes Florida different? Florida is underlain by limestone. And as you know, in humid environments, limestone will dissolve, creating what are called solution features. As naturally occurring fractures in limestone are enlarged by solution, they form caves. If the caves get too big or they form too close to the land surface, the overlying ground collapses to form lakes. When a landscape is dominated by lakes, caves, and other solution features, it is called a karst landscape. And that's what characterizes the geomorphology of much of Florida. But why is Florida's landscape so different? Why is there no coastal plain or Appalachian uplands? Well, it turns out that Florida is a piece of another continent. It was sutured onto North America roughly 360 million years ago, after the formation of the Appalachians, when rifting away from Laurasia began. Florida stayed attached to North America. So thanks to the distinctive bedrock geology, Florida has a very different landscape, more like the northern part of South America. Another interesting landscape is the Black Hills. The Black Hills are a spectacular upland that seems to pop out of the Badlands. How did that landscape come to be? Is it part of the Rockies? Well, it turns out yes and no. The hills were in part formed during the Laramide orogeny, a period of mountain building that also affected the Rockies, occurring from 80 million years ago to 35 million years ago. But the Black Hills are also different. The geology of the Black Hills is a lot like the geology of eastern South Dakota. They're on the edge of the Precambrian Shield, which has been covered by sediments that accumulated from 300 million years ago to 250 million years ago. But more recent volcanic activity, it occurred 50 to 30 million years ago, resulted in an essentially vertical uplift of those rocks. So at the middle of the uplift, there are rocks of the Precambrian Shield, while the younger rocks are draped around it. The Black Hills have been called an island in the plains, and they are great geomorphology. Finally, let's go to Oregon and Washington. In the eastern and central regions where the scablands really command geomorphologic attention. As I mentioned, the Columbia Plateau was created by flow upon flow of lava. The term scablands was used by early settlers because the region couldn't be farmed. The soil was too thin and the weather too dry. What makes this landscape interesting is that during the last glaciation, an ice-dammed lake, Lake Missoula, drained catastrophically over and over again. and torrential rivers carved the scabland. These multiple events were caused by the repeated cycles of glacial advance, the blocking of Clark Fork River, and the creation of Glacial Lake Missoula. As the lake grew larger, the ice dam would be floated by rising water. Once that happened, the ice dam would break up and release the water from the lake. The water would drain, the glacier would re-advance toward the south, and the lake would start to fill up again behind the newest ice dam. The release of the water resulted in catastrophic floods, eroding 50 cubic miles of the underlying basalt and depositing sediments up to 500 feet high on the valley walls. The result is a landscape so unique and so oversized that it still boggles the mind today. But when it was first studied by geologists, it shook the very foundations of geomorphology. How could anything this big happen? No one had ever seen floods of this scale. In the 1920s, J. Harlan Bretz mapped this region for the Geologic Survey, and over time, and a lot of field work, he realized what was going on, describing it as the channeled scablands. Bretz came up with a theory that the landscape of channeled scablands was the result of a mega flood. But when he presented his theory and his evidence in the 1920s, no one accepted it. Yes, the features look like river features. Yes, the landscape looks like fluvially carved valleys. But where did the water come from? Why were the features so large? No one believed him. I always tell students that J. Harlan Bretz is a role model for beginning geologists. Through hard work and by keeping an open mind, he was able to visualize geomorphic processes of unheard proportions. Over time, scientists grew to realize that Bretz had been right all along. It's an inspiring tale from geomorphology that gets to look at your own landscape with fresh eyes. And that's the key to understanding geomorphology. When looking at a landscape, describe it in ways that envision a history for developing the features you see. It'll be a story that includes thinking at all scales, from a single landform to landscapes to geologic provinces. You take into account the combined effects of tectonics, rock types, climate, topography, time, and maybe even plant and animal life. Why landscapes look the way they do is a great way to begin thinking about geology.